Welcome to The Explainer. Today, we're diving into something kinda spooky in the world of artificial intelligence. We're talking about a hidden glitch, a flaw so small it's literally invisible to our eyes, but it's powerful enough to completely fool some of the smartest machines we've ever built. We're going to look at why this happens and then explore a brilliant solution, how researchers are teaching AI to essentially vaccinate itself.
So that brings us right to the heart of the matter, the big question. How is it even possible for a tiny, almost imperceptible change to an image to make a super advanced AI get something totally, catastrophically wrong? It really does sound like something out of science fiction, but believe me, it is very, very real.
Okay, so let's just look at an example. On the left, you've got a picture of a handwritten 9. A typical AI looks at that and, yep, correctly says, that's a 9. But now, look at the image on the right. All we've done is add a very specific, very faint layer of what looks like static. To you and me, they look almost identical, right? But to that same AI, it is now 100% convinced it's looking at a 7. It's wild.
And look, this isn't just some funny party trick for computers. This vulnerability has massive, real-world consequences. Just think about it for a second. An autonomous car that mistakes a stop sign for a 60-mile-per-hour speed limit sign because someone put a specially designed sticker on it. Or a facial recognition system at an airport being fooled by a pair of glasses. As we plug AI into everything, from detecting computer viruses to diagnosing diseases, this invisible glitch becomes a really serious security threat.
So how on earth is this even possible? Why are these incredibly powerful systems so brittle? It really all comes down to the way they learn.
Probably the best way to think about it is this. Normal AI training is like cramming for a huge exam, but you're only using the official practice questions. You get incredibly good at answering those exact questions. You know them inside and out. But the second the real test throws you a curveball, a question that's worded just a little bit differently, you're totally lost. The AI has memorized the patterns from its study guide, but it hasn't learned the actual subject.
And that curveball, it has a name. It's called an adversarial example. It's an input that an attacker has deliberately designed to exploit that exact weakness. The goal isn't just to make a random change. The goal is to find the tiniest, most subtle tweak that will push the AI over a tipping point and force it to make a mistake. And here's a visual of why that works. On the left, you can see how a standard AI thinks. It draws a simple, straight line to separate 9s from 7s. An attacker just has to find a 9 that's already close to that line and just nudge it over. But a truly robust model, the one on the right, learns a much more complex, squiggly boundary. It's way harder for the AI to learn, sure, but it means an attacker has to change the image a whole lot more to trick it into crossing over into the wrong zone.
So the problem is clear. Our AIs are vulnerable. So what's the fix? How do we get them to build that complicated, secure boundary? Well, researchers came up with a really elegant idea, and it's one that feels surprisingly familiar. They decided to give the AI a vaccine. And I mean that almost literally. Just like a vaccine for a person introduces a harmless version of a virus to teach your immune system how to fight it off, this technique, it's called adversarial training, shows the AI the exact kinds of attacks designed to fool it. By seeing these tricky examples over and over again during training, it starts to build up an immunity.
So here's the play-by-play. First, you start with a totally normal clean image, like our original 9. Then you unleash a digital attacker whose only job is to find the absolute best way to mess with that image to make the AI fail. After that, you go back to the AI and you show it both the original and the attacked version, and you tell it, listen up, these are both 9s. You need to learn this. And then you do that millions of times.
This whole process evolves into something much more sophisticated than just showing it a few bad photos. It becomes a structured, high-stakes game between two powerful opponents.
Now, in the world of math and computer science, this game has a formal name. It's called a saddle point problem, or a min-max optimization. I know, that sounds super technical, but the idea behind it is actually pretty intuitive. It's just the formal way to describe a tug-of-war, where two players with opposite goals are constantly fighting each other until they reach a stable balance.
Let's meet the two players in this game. First, you've got the attacker. Its goal is to maximize the AI's error. It looks at the AI and asks, what is the absolute worst thing I can do to this image to cause the most confusion? Then you have the defender. That's our AI model. Its goal is to minimize that exact worst-case error. It tweaks its own internal network to make sure that even the attacker's best shot isn't good enough. This constant battle is what forges a truly robust AI.
Okay, so does it work? What actually happens when you put an AI through this kind of intense competitive training bootcamp? Well, the results are pretty amazing.
But first, one really crucial discovery from the research. To learn those super complex, squiggly decision boundaries we saw earlier, the AI needs more capacity. And what that really means is it needs a bigger brain, more layers, more connections. Defending against these clever attacks is just a fundamentally harder problem than recognizing clean images, so the AI model itself needs to be more powerful to keep up.
And here is the payoff. Just look at this. When you hit a normally trained model with a really powerful attack, its accuracy completely collapses. It drops to less than 1%. It's basically just guessing randomly. But the model that went through the adversarial training, it stands its ground, maintaining an accuracy of nearly 90%. That's not just an improvement, that's a total game changer.
Let's just pause on that number for a second, 89.3%. And remember, this isn't its accuracy on easy, clean pictures. This is how well it performs while under a direct, powerful attack that was specifically designed to make it fail. It shows that this vaccine isn't just a band-aid. It fundamentally rewires the AI to be more resilient.
So what this research really gives us is a recipe for building safer AI, and it comes down to two key ingredients. First, you need a really strong adversary during training to keep things challenging. And second, you need a neural network that has enough capacity, a big enough brain, to actually learn from those challenges.
And in the end, the researchers wrap things up on a really hopeful note. This isn't some far-off dream. We have the tools, we have the understanding right now to start building AI that isn't just smart, but is also secure and trustworthy. That invisible glitch might still be out there, but now we finally have a map to fix it.